So this is week 9 of NPTEL ME23. So today we'll be discussing on motion and trajectory control. So this generally when we talk about control, we are talking about feedbacks and feedback loop, and we'll be interested in deriving the transfer functions from, let's say, for proportional, integral, and derivative gains, right? So before we get into problem solving for this week, we'll go through the lecture content once, and then we'll proceed with. Okay. Yeah. So this week, okay, I presume most of the questions will be related to you have to make a MATLAB code, and you have to run a couple of them. It's more of simulation than conceptually deriving something. Yeah. So generally, when we are talking about trajectory control in robot manipulators, we are talking about the end effector position and few of the parameters like not only end effector position, we are interested in end effector's position with respect to time, right? So it needs to be there at a certain velocity, at a certain acceleration. That is what we are interested in. And then there is the second aspect, that is the end effector must be imparting some amount of force, pressure, or let's say, yeah, force and pressure. Maybe pressure is little vague. Force is what we are interested in, right? So all of these would boil down to end effector, where the end effector is at a given point in time. So based on that, you would get your joint position, velocity, acceleration. Then there are other terms also: jerk, snap. They are higher order derivatives of acceleration. And yeah, derivative of acceleration is jerk. Derivative of jerk is snap, right? So you would be interested in finding all that. Although in manipulators, generally we stop till jerk, right? So here, what we are interested in is making a trajectory, right? And also following that trajectory. So the approach that we do here is to minimize error, and that is why we would require something called a feedback, right? A feedback is generally to tell you where you are, and the trajectory is where you need to be, right? The difference between them is your error, right? So there are multiple schemes of doing this. Anyway, we'll skip all this, and we'll go on to the first way of looking at angles of your joint with respect to time. So one such way is piecewise linear, that is piecewise continuous. That means that the continuity C1, C0 continuity is made entirely in this line, and there is a C1 discontinuity but C0 continuity, right? And then it follows another line. So this has another C0 and C1 continuity. Then C0 continuity is maintained here, C1 is not, and then it proceeds. So this is a piecewise linear way. And then to look at this, you would find that your theta dot would be something like the slope of this, that is constant in this trajectory. Then there is, you see a sudden change, and this is negative slope, and such a thing going to motor would make it a lot of things, lot of wear and tear. You would get a lot of heating issues, and this is the kind of things that we need to avoid, right? And if you see at acceleration, it is abrupt, right? It's totally zero in a small region. It is actually infinity. It goes to infinity. This line tends to infinity. How would you give an infinite acceleration, right? Negative infinite acceleration. So these are the things that we need to avoid, and we'll try to, have theta dot, theta, and theta double dot as a continuous function, right? So a constant acceleration would give you a quadratic equation in theta 1, and linear in theta dot. Sorry, theta would have quadratic, and theta dot would have, uh, yeah, yeah, it's okay. You go on. Right. Yeah, so we would have that, and then, yeah, so we would want our theta to be continuous, theta dot to be continuous, and theta double dot to also be continuous, right? We don't want singularities. That is what we mean by it, right? So one such trajectory is cubic, obvious, right? If it is acceleration being linear, how will you decelerate, right? If acceleration is constant, like if you take for the case of g, can you go against the gravity? Yes, obviously you can, but then you have to give uh, a jerk or an acceleration that is equal to g, right? So you would require a third order system, right? So this polynomial is of third order, and with this you would see that we would have our acceleration, right? You can see acceleration is linear, right? It can be constant, that is a3 will be 0, right? And this means that it is a constant jerk that is applied onto the joint rotation, right? The motor that is causing the joint to rotate is giving you a constant jerk, right? So that is how you can look at it, zero or constant jerks, right? So this is one of the way of having your trajectory, and you can have higher orders if you have a fluctuating, acceleration and all that. But anyway, let's just keep it this way. Yeah, so here you would see you can have cubic trajectory with via points, or you can say waypoints. The trajectory has to pass through those points, right? And in those points we might encounter some singularities. That is, when we say that it has to follow a certain velocity at a certain time, you see you get a kink there, and there is where you have your jump in your acceleration. And this is still fine. We can give a ramp, and we can eventually get over it. But anyway, we would want to avoid these kind of discontinuities, right? So what does this mean is that the motor was decelerating. Now suddenly it has to accelerate to this point, and then it has to decelerate from there, right? So that means that this point is what we are interested in. We want our velocity at this point to satisfy certain uh, value, right? So yeah, so this is angular velocity. Let's just keep it that way, theta dot, right? Yeah. So this is again multiple cases to it. Here you can see there is an acceleration c0 continuity, but c1 continuity is lost. That means there will be a jerk, discontinuity in the jerk that is applied onto the um, link, right? So onto the joint, sorry. Yeah. So we will also skip this. This is a couple of things that you can go through, right? We will come back to, okay. So now we'll enter into controls. So for a control over a single link, that is what we will discuss first. Most of your questions are based on this, and we'll see now. There are two thetas, that is one that is desired and one that I No. So that is from a trajectory that we have seen previously, right? Now, yeah. So now the theta d is what I'm interested in, and if you see a link for a link, the rotation theta I of that link, right, is related to the motor by some factor, right? So here you can see this is the gear ratio or something like that, right? And then you can substitute this theta I in terms of theta of the motor, right? Theta L, this is actually L, right? Is the theta of the link, right? Rotation of the link can be related to that of the motor, and your uh, mm, this is your inverse dynamics equation, right? Yes. So this is your Euler-Lagrange equation, and you can substitute it there, and you would get in terms of your rotation of your motor, right? So here is the factors, that is inertia of the motor, friction that is there in the motor, that will again, yeah. So this is a second order system which is dependent on viscous damping, right? So this is like yeah, here they have given it as viscous friction, but you can recall this equation from vibrations. You would have a double dot term, theta dot term, that is generally associated with your damping, right? Here it is the friction on the motors, and here you wouldn't find a theta component, only because this is not a simple harmonic motion or a damped harmonic motion, right? So there is where this equation comes from, and you can see this is for the second link, yeah. So this is the equation for the second link where the torque is applied onto the first link, right? Because they are serially mounted. Yeah. Oh, okay, one second, I think, yeah, the one denotes the torque from acting on gear 1 from gear 2 and the link. Okay, there are two gears, I guess. Yeah. So there are two gears that are transmitting this. One gear is obviously from the motor, the other would be attached to the link, right? So this is not for a two link system. This is rather for one link. So there are, you can see, a couple of uh, um, gears. All of that will add up. The torque due to those gears will add, right? Yeah. So here is our equation of motion from the system, right? So this Jm is from the robot, n square J L is from your um, yeah, sorry, Jm is your motor, Jl is your link, Fm is from your motor, and Fl is from your link, right? So this becomes your equation of motion for the system, right? So here you would yeah. So a motor, generally many motors have their torque profile, and they give you a relationship of how the torque is generated by the motor depending on your input current, right? Generally these are inductors, so that's why you have your current as your input for the torque or the force that it gives you, right? And the back EMF from such a coil rotating at a certain um, angular velocity is given by this expression, where kg is your EMF back constant and kt is obviously your torque constant, right? So this torque constant will have all the design elements of your motor, right? So your motor might have some thickness, some coil windings, all of that is encapsulated in the kt, right? So the dynamics of the motor here is that if you look at the motor, the circuit is that you have an inductor, you have a resistor, uh, yeah, resistor, and then you have your back EMF, which joins with your total voltage applied across the motor, right? So here for small, I didn't know that, but for small DC servo motors, LA is small. uh, I mean, the fact that LA is small, I did know, but we would ignore it. um, at Yeah, this is the first time I'm seeing it. Anyway, so taking this as it is, La is small, so this is the inductor of the yeah, inductance of the armature, and this can be ignored for smaller DC motors, right? From that, we substitute it here, right? What was this? This was torque from motor. I'm going back. You can see torque from motor. Torque from the link, we'll come back to it, right? This is substituted here. So this is the torque from the motor, and this becomes our equation of motion of the motor, right? Of the link, sorry, because we already have Jm, right? So this can be made in a compact form where you see this entire term, the inertia term is encapsulated as J. Friction, right? Viscous friction is encapsulated as F. You need to know this. Why? Because we will come to an expression that is the transfer function for such motors, right? So this is equal to K VA, right? This is VA, and K is some term that comes out from this expression plus TD. TD is generally the kind of disturbances we term it as disturbances that is given to your system. Like here you can see n times of torque on uh, link, right? So what is torque on the link? So it is either you're applying some force onto your link, and that is why you have got your torque on the link, right? Yeah, torque on the link, right? So this is your disturbances. We will have certain questions with such disturbances, and then we would see how to solve them, right? So here comes our first thing. How do we get our transfer function, right, for our motor? So what we do is take it into Laplacian domain, right? Yeah, I think someone has joined. I'll just give you a recap. You know, a recap of what I've just covered. So our objective is we have got our trajectory. You were there till trajectory. So here we want to go in that trajectory. So now we are concerned it at the theta d, that is the desired theta, right? We want to look at it, but what we are going to see is theta, where we are. And how do we find where we are? That is using feedback. So that we will come back to later, the physical systems that are involved in getting you the feedback. The equation of motion of our, for a single link, or let's say even for a robot, has to be transformed from our link rotation to the rotation of the motor, right? So motor is attached with a lot of things, like you can say it is attached with couple of gears. Those gears transfer the desired rotation rate and rotation to the end link. So here is where theta L is the theta that we have derived from Euler-Lagrange equations. That is n times, that is the gear ratio, n times theta m, right? So if this rotates by 60 degree, this would have rotated for 5 times to get it 60 degree, right? So likewise, this is constant; it doesn't change. So you would find theta dot and theta double dot also being the factor of same, right? So the equation of motion from the motor to gear one, right? There will be two gear that would mate and transfer the motion. So the equation of motion from gear one would be something like this. This is the torque from the motor, and T1 is the torque from the gear one. Similarly, you have that of gear two, where torque one and torque two is applied onto the gear 2, right? Torque 1 is from the previous gear, right? From there, we get an equation of motion that is with respect to the link parameter, that is JL, inertia of the link, inertia of the motor, uh, viscous friction of the motor, and then that of the link. So together we have that equal to our torques from motor and the link. Now this link torque is something that is either as a disturbance, or when we apply force onto a link, that is what we mean by torque on the link, right? So you can make a force into a couple system, right? So that is how you need to look at it. But here primarily we see TL as disturbances, right? We will come to that expression in a while. So here every motor has a torque profile, right? How it is related with current. They are generally inductors, right? So that's why they have a linear relationship, right? But different architecture of motors will have a different relationship, right? Then the back EMF from this motor, because this motor is rotating, the back EMF that is generated is given by the back EMF constant times the rate rotation, right? So then we get the dynamics of the motor, which is something like this. There is an inductor, there is a resistor, there is back EMF, this total joining to form your the voltage applied across the motor, right? So we plug that here, right? Where is this? This is torque of the motor, right? We plug it here and we get our equation of the dynamics of the motor, or equation of the motion of the motor in a compact form. We convert this compact form in Laplace domain, right, to get our transfer function, right? So this is our transfer function from yeah. So this is our transfer function from um, theta s, right, or theta to your voltage that is applied, right? So how is this done? So you will have to go back. You have to find a inverse relation because this is in terms of time, right? It is in time domain. We are taking it to frequency domain. We would integrate this, right? So this is Laplacian. Sorry, it is not inverse Laplacian. Inverse Laplacian will be when I have this, we go back to time domain, right? So we yeah, yeah. So we integrate this function, and we would get that in a domain, in a frequency domain, that is in this form, right? So here is your blocks. So this is your voltage applied, and this is the transfer function, and then you get your theta rotation, right? Yeah. So this TD is from your disturbances, right? So you can see where I missed. Yeah, this TD is basically your torque from the link, right? So if you take it as a force coupled system, you would say that the force that I'm applying on the link is the torque on the link. You can convert it that way, or there is some torque, counter torque given by the link, because it's a mechanical component. It might have some, something latched onto it, something grinding over it. N number of things can happen, and that is your disturbances, right? And here is how your disturbances act with your uh, voltage, right? With your voltage applied, yes, with your voltage applied, yeah. So if I change this voltage applied as the theta that I want to go with, right, this 1 by k term will vanish, right? Because TD would be directly, torque, and that would be uh, with theta, right? In terms of theta, and this 1 by k term will go away. Okay. Anyway, so this ds is what we do. This is what is our concern, right? What do I put here such that this entire thing, right? This feedback loop, when it closes, right? When it closes, Yeah. So yeah, okay. My bad. Even when you change it from Vs to theta d, right? You still have 1 by k term, right? That was my bad, right? You still have 1 by k term. Yes. So this is what we are concerned about, the controller. What do we put here such that my desired rotation is reached, or rotation rate is reached, without much of oscillation or much of steady state error, right? So what is a steady state error? We will come to that later on, other slides, right? um, yeah. So here you can see how it's derived, right? We'll just skip this because this is trivial derivation. Come back to this. So this is your first order system, right? In your first order system, you generally have k divided by j s plus f. For your second order system, you have 1 by s, that is an additional factor that comes in your transfer function, right? So here you can go through this, but however, I'll just skip this and go to the second order system. In a second order system, you would find an s that is multiplying, uh, you know additional to this. We'll derive this how it comes across. We'll derive this, right? So your transfer function, here you can see in the second order open loop transfer function, your yeah, in second order open loop, you have your transfer function as k divided by s times js plus f. We'll see how this expression comes, right, later on. I'll switch to my pen paper mode, and then we will see how it's how do you get that, right? But remember this structure. Sensor will always have a feedback which is 1 to 1, right? So whatever it get as theta s, it will be given as theta uh, back to the system where it will compare, right? So you can have a factor of 2. If your sensor already has a factor of 2, you will have 1 by 2 here, right? You need to have theta d minus theta, right? The norm of it. Anyway, moving forward, we would have so we would introduce something called damping here, right? So this is for undamped system where your epsilon is under 1, and that for where it's equal to 1, it's critically damped, and for that is greater than 1, this is back to vibrations, right? It will be over to 1, right? Now we will introduce something called a derivative control, right? Proportional, along with proportional, we'll put a derivative block. So the derivative block, proportional was just a constant that was multiplying with the transfer function, but a derivative will take away one order from the system, right? So it would be kv or kd times s. So it will take away one order of the system, right? Because it's a derivative, right? If you have a second order polynomial, the derivative of it is first order, right? So the order reduces. That's why kv times s would come, and an integrator which increases your order will have 1 by s term. It will be ki by s, right? So I'll just quickly go. This is how the expression comes out. We'll derive this also, how this expression comes about, right? And then that of I, you can see it is 1 by s, right? So this is for a specific control where we don't want some variation. So this tv is a time constant that we choose, right? We be careful of choosing it, right? And also we don't want skv term, because skv is reducing your order. The moment you have your order that is reducing, you will have oscillations, right? So because of, I guess I skipped that. Yeah, I skipped that part. Okay, yeah, here you can see increasing kv decreases overshoot, but settling times becomes larger. right? It keeps on oscillating. That derivative introduces some amount of damping, right? But that damping can have overshoots, and those will have oscillations, right? So that is the role of skv. So we wouldn't want skv, rather we will introduce kv by 1 plus tvs, right? So here if you see, the effective order is something like that of kp, right? So with that, we would get our PID, feedback control, right? And this is for digital systems. I'll conveniently skip it. And the extension of control using single link to that of multi-link is further discussed. So I will leave it here. This is again the same thing that we have went through. Just the rigor is maintained, and it is done for other links too, right? So we'll now switch to pen paper mode, and then we will also solve certain MATLAB problems. I'll show you how to plots these transfer functions that you have made, that you have either derived or uh, you know you're given to, and you're asked to change some parameters, and how do you plot it, right? Great. Okay. So now let me just join from my tablet, and then I'll get to you. Yeah. Mhm. Are there any doubts till now? So this is a good time. We
No,
can discuss some doubts. Yeah.
no doubt, sir.
Okay. All right. Right. Okay. Hmm. That's okay. Let me just close my mic here. Yeah. Oh. Okay. What should I be doing? Yeah, this is fine, I guess. There is a way. It's okay. Yeah. This must be better. Yeah. Fine. Mhm. Okay. Right. Wonderful. So we have our first question with us. So the thing they have asked here is that you are given some parameters, right? So these are your boundary conditions of your trajectory, initial and boundary conditions. This is an initial condition, boundary conditions on trajectory, right? So what we are asked here is to find all the coefficients of the cubic trajectory. This is a fairly simple question. It is for 4 marks, I guess. So what we do here, we know that it is a third order system, that is cubic equation, right? First, what we would do, since we are also given uh, the Neumann conditions, that is your rates are specified, right? So we would take the derivative of this equation, we would get something like this. Now we substitute all these conditions that we have, that this should follow, right? So what would it be now if I have theta 0, right? So I'll get a naught, which is equal to 0. right? Now if I have theta 3, that will be 3 into 3, 9, 9 into 3, 27, 27a3 plus 9a square plus 3a1, right? Plus a0, which is 0, right? Wonderful. This is equal to 60. So I'll just take this off, make it equal to 60 degrees, right? Now, for theta dot at 0, it is 0. So what will it be? A1 equals 0. So A1 also goes away. That's 0, right? So we'll just take it off, highlight and take it off, right? So this is not there, right? Now we'll go with theta dot at 3, right? That is also 0. So it is starting and stopping there. So there is a phase in between where it is accelerating, then it is decelerating, right? So what do we get here? 3 into 3 into 3, that's again 27a3, right? This is right. Yeah, plus 6a2, right? A1 is 0, right? What we have got here. So I'm not putting it, which is equal to 0 again. So what we'll do now is just subtract this equation. You would get plus 3a2 equal to 60 degrees, right? That's right. Yeah, it is right. A2 will be equal to 20 degree per second square, right? This is wrong. S square, right? Then what we do now is find A3, right? That is the only thing left. A3 will be equal to minus 120 by 27, right? By 27, 6 into 2, yeah, minus 120. Yeah, okay. This is 9, 4, 4, right? So you will have 36 is 4 times, right? Minus 4, 4 by 9. Okay. This should be degree per second cube, right? This is degree per second, and this is degree, right? So how does our equation look like? Theta of t is minus 4, 4 by 9 t cube plus 20 t square plus, oh, there is nothing else, right? So you get theta dot. It's just repetitive, but I'm doing it nonetheless. Yeah. So I can directly do it here. B minus 40 by 3, right? T square plus 40 t square t, right? So you need to plot this in MATLAB. So you're asked to plot this. This is a subjective question, right? You're asked to plot this. Not theta t and theta dot, right? So now we'll come to controls problem, where we would look at how, so this is a second order system, right? How that transfer function, sorry, the effective transfer function, that is your theta by theta d, right? How did it come about, right? First we will find that. So this is second order, right? System, right? So you know how this has come, right? So I'm just leaving it there, right? So how do you make out of this such a diagram? Is that you look at it this way. what is going out here, right, is equal to this, sorry, what is going out here times these things. Now whenever you have nothing like a comparator in between, they are always a product of the functions. So what is going out here is going through a product of something and then coming out, right? So what is coming here? It is theta d minus theta, right? Theta d minus theta is coming in, and then it is getting multiplied with this, and it's equal to theta, right? So first we will derive for only proportional, then we will introduce integral and derivative, right? Kp is proportional gain, right? Kv or Kd is derivative gain, right? Ki is integral, right? So assuming only Kp, right? This block is only Kp, we would get theta d minus theta. All of them are in frequency domain, right? Yeah, times Kp times K S Js plus F equals theta, right? So now we'll take theta all in one side, all onto one side, and keep theta d on the other, so that we can take a ratio, right? So we would have theta d k kp divided by s into js plus f, which is equal to theta js square plus fs plus kkp, yeah, yes, divided by sjs plus f, right? So we would get theta by theta d is equal to kkp divided by js square plus fs plus kkp, right? Similarly, we will do the same for, where is it? Yeah, just move this aside. We will do that for a derivative control, right? So same rigor, theta d minus theta times kp plus kvs, right? So what is this? This is your ds. This is your controller transfer function, right? So that is what will get added here. This is d of s. This is g of s. This is your transfer function, right? Or else you can say tf of s, whatever suits your liking. Yeah. So this is your transfer function of the controller times k divided by s js plus f, which is equal to theta, right? We'll do the same rigor again. T kp plus kvs times k divided by sjs plus f will be equal to theta js square plus fs, uh, yeah, plus kkvs plus kkp whole divided by sjs plus f, right? Now you can see this go away. You would have theta by theta d is equal to kp plus, okay, kkp, plus kv ks divided by js square plus f plus k kv times s plus akp, right? Similarly, you can do for your integral control, right? You would get another expression like this. Anyway, we'll just stop here. So yeah, we'll just stop here for this question because look what they have asked for, right? So we are given this J, that is the combined inertia of your motor and link, right? Of your single link manipulator, it is your combined inertia. K is what was K? Um, K was, wait, we'll just refer to. All of a sudden, I forgot what was K. F was your friction terms. Yeah, K was that from your back EMF, right? So it is from one second. Your torque, right? Your back EMF and your resistance, right? So that K term is something like you. Okay, one second. K is something like um, all the terms that is a physical nature of your motor, right? It's the build of your motor that is encapsulated as K. It is how much winding has gone in, number of turns, the build of it, that is your structural response of it. All of it is combined in K, right? So yeah, so the K term is basically your motors or your links build, right? So anyway, we will switch to MATLAB and we'll show how to do this, right? So for a step response, we generally have the step response in that of frequency domain is 1 by s, right? So when you have theta d as a step response, what does that mean? Theta d at t less than t naught, less than not equal to, it is 0, and then it is some value, let's say alpha, when t is greater than equal to t naught, right? How does that graph look like, right? So I'm taking this as negative time. This is somewhere, sorry, not negative time. Let's just keep it this way, right? It's going to look like a function like this. Yeah. So if you follow this rigor, you make it minus t times 1 dt, right? If you integrate this, you get 1 by s as the function, right? The Laplace. When you take Laplace over this function, you would get 1 by s. Yeah. Yeah. That's in. Yeah. So I'm switching over to MATLAB. Before that, I'll just check it. Okay, fine. Uh, we will switch on to this. I hope I'll just stop presenting from the tablet. Yeah, this is not visible. How is that? Right. Okay, I'll reshare it. Yeah, this is all that we had done back then. Okay. Yeah. So looking at the problem, we have theta is that entire transfer function times 1 by s, right? So that is because we have a step response. So what we have been given is that j is equal to k is equal to f, kp is 1. So we'll just write down those things. 1 capital K is equal to j, f is equal to k, right? Kp is equal to 1, right? Now we are going to have symbolic variables, right? Why do we need them? Because we have a function that is a function of s, that is our domain frequency or frequency domain, right? Now what we would do is vary kv, right? So that kv is being varied. So let me make a comment. Vary k k so v from 0 to 2 by a step of zero point 0.5, right? So now since you would see our f equation, I'll just mention that in comment. Capital of f, yeah, of s equals, this is a comment, it will not execute this. Let me just copy down that equation that we had derived. K times kp plus plus kv times k times s, right? Entire thing divided by j times s square plus s times f plus kkv plus k times kp. So now we will have, how many variations are we doing with respect to kv, right? If you see, we are doing 5 from 0, 0, 0.5, 1, 1.5, 2, right? So it is 1, 2, 5, right? And then, yeah, okay. Yeah. Now what we will do is substitute this value, right? To substitute that value, what we will do is make kv of I, right? So we'll declare an empty matrix before kv of I, or it's not required, right? Let's just keep it that way. We'll make it complicated, sorry. Yeah, I minus 1 times the step. What is the step? Zero point 0.5. Yeah. So now what we will do is take f, right? F. How do we do that? I Laplace. Is it CE or SE? How did they derive it? It should be CE actually. Right. How is it that MATLAB is using it? CE. Yeah. Okay. So we have capital of F, right? So first we have to define it here, right? I was Now we have it in time domain, right? So we also need to give another parameter time here in the symbolic declaration, right? Frequency domain t time domain, right? Now we have to vary our time so that we can get a plot of it, right? So we will vary this from 1 to 100 points, let's say, right? So 101, that makes, yeah, 101 points, so that we get some even number, right? So again, you can see those underline over for loop because it's not ended yet. So we'll end it in some time. Before that, what we will do is declare time as a empty matrix so that we can get a array of it. We will directly plot it instead of taking each point and plotting it. We'll make an array of it and plot it. So this will be I minus 1 times, let's take an increment factor here, that is 0.1, right? So every iteration of j is computing for delta 0.1 seconds, right? Now what do we have? Fv new variable is equal to substitute the expression for the t that we have put just now, right? T of j in time inside the equation f. So we will get the value at that function. So this will also vary along j. That's why I'm making it another empty matrix. It's just convenient to use empty matrix. That's the reason why I'm using it, right? Please don't be tempted to use it again and again. You can, once you learn how to vectorize your equations, it will be much easier. Figure 1. Now I'll plot them because see, at the end of j loop, 101 elements I would have got for this. Now the next ith loop, this will again refresh. This is refresh. Every loop it refreshes, right? Please stop me and ask questions if you have any doubts in the code, right? Till now, the logical flow of the code, right? Now I'll plot them x versus y. So what will it be? X is t, comma fv. Now since I have plot in one figure, I want all this variation of kv to be plotted in the same figure. That's why what I'll do is put a hold on command. It will not close that figure. will wait for me to close that figure. So what I will do in the end, I want to label those things, right? So I can put a legend command here where I'll say individual of them, what are they, right? So are they K or kappa? K, right? K underscore V. So you can put a backslash so that V will go underneath KV, right? Comma, okay, what is it? Equal to, sorry, 0.0 kappa underscore, sorry, K underscore V is equal to 0.5, comma, backslash, oh, I didn't put backslash, K underscore V is equal to 1.0. I'll just copy paste them. 1.5, 2.0, right? Now we will do a hold off, right? So let's try and run this. uh, Inverse Laplacian. Oh, here I missed a L. Okay, yeah, that's error. It will wait for some time. Hmm, what's wrong? No, it's still doing. It's just slow. The computer has become slow. Where is the graph? It's okay. Okay, I think I made a mistake. It's not I here, it's rather J. Right? So I guess it couldn't. No, 1 second. I don't think this is right. Somewhere I've made some mistakes. Right? Let me just check it out. Hmm. Increase the time. Access axis. And yeah, it is much better. Why is it going negative? It shouldn't go to the negative. One second. Yeah, I've made some mistake, which I am finding a little. Yeah, yeah. I've just recalled. Like, actually, I'm comparing it with a code I had made before the class. We had forgotten that this is the transfer function, which will also have a multiplication factor here because you have a step response, right? We totally forgot that one. So S finds this. Right? Now, just take it off. Right? Yeah, this is the response. You should get okay. What happened? I'm still making some mistakes. Yeah, it's a mistake. Mhm. KBK, where is J square S plus KBK times KP? Yeah, F. Now we get, yeah. So I should be getting value. Let me just check. This is fine. This is also fine. Mm-hmm. Okay. Where is the error? F is equal to K. I'll just put this as values. No confusion that way. Takes quite some time. This is correct. Why is this going overshoot? Mm, now, this J minus 1 is 0.1. Uh-huh. One second, I'll just substitute the value here. Right? 1. So it's 1 again. J is 1. This becomes 1 plus kV. This is 1. Right? It's taking out confusions. Control C, Control C. Mm-hmm. Yeah, I done some mistake there. Right? We should be able to find it. Okay. I think here J star S square, right? I think that must be the problem. Let me just check it. Right? K star plus K star K P. Yeah, let's check it if that was a problem. Anyway, it should superimpose, right? Stop, stop. CLC, CLF. Uh-huh. Okay, I got it. What's the problem? It's quite stupid though. We are replacing F here. I think that is the problem. Let me just put G here. Quite a stupid mistake. Anyway, that's why it was taking time also. Yeah. Right. Okay. So this is, I guess, the response that we should be getting by increasing kV, right? You can see the moment I increase kV, this oscillation dies down, right? I'll just blow it up. Yeah, this oscillation dies down as and when I'm increasing kV, right? You can see the kV value. When I increase it, these oscillation overshoots are dying down. Right? So I made a really foolish mistake here. So that's why it was not. Yeah. So we'll move on to the next question. I'll be going back to my writing tab and oh, okay. All right. So are there any doubts from this code? Are there any doubts I can present again? I forgot to ask for doubts. Yeah.
No, sir.
Yes. No.
No doubt, sir.
Okay. The other one is also similar to this one. It's the same thing, just that we'll derive, you know, uh, that for integrator. Right? So we also have a disturbance here. Right? You can see we also have a disturbance. How do we do it? Go back to the basic. theta. Okay, actually, this is wrong. Right? If you see from the lectures, right, theta d comes after your controller. Right? So this is plus plus. Here comes your TD by K. I've already multiplied with the gain, so just assume it that way, right? Yeah, how do we proceed with this? Again, TD, sorry, theta D minus theta. Again, from here, this is what is out times KP plus KVS plus KI by S, right? Then there is this entire term is added with this. Then there is your g of s. G of s is what? A s into js plus f. What is this equal to? Theta, right? This is our expression. I'll just expand this. You get theta d minus theta times kp kvs plus ki by s times k divided by s into js plus f, right? Plus td divided by k cancels off, that's why js plus f, yeah, is equal to theta. Perfect. Now we'll take separate the terms out. So we'll write it like this. We'll not make a ratio anymore. We'll make it something like this: js square plus fs plus kkp plus kvks plus kik by s, right? Yeah. One goes there, this goes up, yeah, the entire divided by s js plus f, right? So you can multiply and divide by s, right? Or yeah, should we do that? Yes. Let it be. We'll just deal with it later. Theta d times kp plus kvs plus ki by s, right? Divided by s j s, k comes here, plus f plus td s j s plus f. This goes off, right? Now let's just write our terms, right? kkp plus kvs kkvs, right? S square s plus ki divided by s, right? Here also we'll make it s square. Is there any point in doing that? Yes. Okay. S square s cube s square s I, right? And then we have d dt, right? Divide this entire equation divided by. So if I just multiply and divide by s, s goes off everywhere, right? This entire terms goes. plus mhm, js cube plus s square times f plus kkv plus kkps plus kki. Yeah. So this is our theta d. Similar to the previous problem, you assume that this one is a step response, right? You multiply it here and then you will get a entire equation. Similar to the previous case, you solve it by varying ki. Initially, it is given that in the previous year, it was given that ki you assume 0 and find out what happens at this point. Then you vary ki to get your response, right? So you will get theta s. You convert that to theta t, right? Inverse Laplacian. Yeah. So I guess these are the problems that you might have some difficulty in solving for this week, right? So if there is any further doubt in this, shoot me a mail, right? I'll be happy to solve it and send it to you. Anyway, so with this, is there any doubt here? Because I did some jugglery here, right? So here and here. Right? I hope that is clear. I'm just multiplying it. I'm just doing it very fast. Yeah. So is this clear? Are there any doubts? We can discuss doubts now.
No doubt, sir.
Okay. Wonderful. Then I'll close the session here. Right. Uh, I'll stop the recording.